On Friday, we introduced the new unit on dynamics, and we differentiated between our last unit and this unit. Kinematics, of course, last unit, the very first day of physics, we defined it as the study of motion without regard to what caused that motion. Okay, we spent a number of weeks talking about constant velocity, talking about the acceleration of objects, talking about the motion of the object, but not once did we talk about why the object was moving as fast as it was, or what got the object moving in the first place. That's dynamics. That's dynamics, where we talk about what caused it to move in the first place. Dynamics is the study of motion, just like kinematics is the study of motion, except it is with regard to what causes the motion. In other words, dynamics is the study of forces. Forces cause motion, so dynamics is the study of forces. Now, we defined on Friday, as well as maybe in grade 8, grade 7, grade 6, I'm not sure when it was you defined force for the first time. It's a push or a pull. And we talked about the two things that a force can do. The first thing is that it can cause an object to accelerate. And that acceleration could include speeding up. It could include slowing down. It could include stopping or starting. It could include even changing direction. Do you know that if an object is going at a constant speed, a car maybe, is going at a constant speed around a turn on a highway, even if it's not changing speed, it's still accelerating? Acceleration is defined as the rate of change of velocity, not speed. Velocity includes direction. So even if you're going at the same speed but changing direction, that's still acceleration. Forces cause acceleration. Speed up, slow down, start, stop, change direction. Forces cause acceleration. But forces also cause deformation. And what do we mean by deformation? Change the shape of something. When a basketball hits the floor, it accelerates, it slows down, and then it accelerates, it speeds up as it goes upwards. But during that process, it also changes shape. When you hit a golf ball with a golf club, if you're good at it, that is, the golf ball, believe it or not, the golf ball actually deforms to a size that is barely half the normal size of a golf ball. For a brief moment in time, the golf ball is squished to barely half its normal size. Yeah. Now, it accelerates pretty quickly thereafter, right? But during that time of initial contact, it's not accelerating, it's deforming, it's changing shape. So forces can cause things to accelerate, and they can cause things to change shape or to deform. Sometimes they do both, as in the case of the basketball or the golf ball. Sometimes they only do one, where is in the case of the force of the wheels pushing on the road, push your car forward, causing it to accelerate. Sometimes it only causes deformation. I push on the wall right now. Am I causing this wall to accelerate? No, not at all. Am I causing this wall to deform? Yeah, a little bit. The wall changes shape a little bit, as does my hand, as the wall pushes back there. Doris, you had a question? Okay. The next term we talked about on Friday was the net force. The net force is the total force, or the unbalanced force acting on an object. If the net force is 0, how can we have a net force of 0? Well, maybe if Nick pushes on his desk, on this desk here, with a certain force this way, and I push with the same force the other way, two forces acting there, but the net force is 0. The total unbalanced force is 0. When you have an unbalanced force of 0, when everything balances out, nothing happens. The object keeps doing what it's doing. If that desk is at rest, it's going to stay at rest as long as we both push on it with the same balanced force. But, keep pushing. If all of a sudden I let go and there's an unbalanced force because Nick's pushing on it, then it's going to start moving. Now, if that desk was sliding on ice and we were both pushing on it with equal and opposite forces, what would happen to it? It would keep sliding on ice at a constant speed. It would keep doing what it's doing as long as the forces are balanced. It only speeds up or slows down when we have an unbalanced force or a net force acting on it. Yep. Excellent. Inertia. This relates to what we were just talking about, right? Inertia is the tendency of an object to keep doing what it's doing. The tendency of an object to resist a change in motion. In Physics 30, we're going to talk about a term called momentum. Momentum is loosely defined as how hard it is to stop something. Inertia and momentum often get confused with one another. Inertia, how hard it is to change the motion of something. Momentum, how hard it is to stop something. What's the difference? Well, when an object is moving down the road at 100 kilometers per hour, it has both inertia and momentum. It's hard to change its motion, and it's hard to stop it. But an object at rest, a big, heavy object at rest, still has inertia. It's hard to change the motion of that object that's at rest, but it doesn't have momentum, because momentum is dependent upon velocity as well. Inertia is only dependent upon mass. The heavier something is, the harder it is to change its motion. The harder it is to cause it to speed up. The harder it is to cause it to slow down. The harder it is to cause it to change direction. The heavier it is, the more inertia it has, and the more it wants to resist changing its motion. The more it wants to keep doing whatever it is that it's doing right now. Static equilibrium. Just a couple more terms here, guys. Static equilibrium. Talked about this just the other day in Physics 30, actually, in the context of electric forces on electrons that are on the surface of a metal sphere. Sounds kind of crazy. It's exactly what we're talking about right here. Static equilibrium means balance. Okay, that's what equilibrium means, right? Taking chemistry class, you know that equilibrium means balance. Static means not moving. Okay, something's balanced, not moving. An object at rest has balanced forces acting on it. Right now, I'm not moving, right? Right now, none of you are moving. Gravity pulls down on you, though. That's a force. There's also what we call a normal force of the ground pushing up on you. Those forces balance. They're not causing you to move. You stay at rest because those forces are balanced. You're in static equilibrium. Balanced forces at rest. On the other hand, last Friday when you were doing this stuff on podcast, I wasn't here. I was driving with our cross-country runners to provincials in Grand Prairie. Driving, set the cruise control at 110 kilometers per hour. Do you think there was forces acting on me? Of course there was. Force of the wheel acting on the road, propelling me forward. There was a force of wind resistance, right? But I was going at a constant speed most of the time. That was translational equilibrium. Okay, everything was balanced. Force is balance. Don't speed up, don't slow down. Don't change my motion. Keep doing what I'm doing. Okay, translational equilibrium, force is balanced, but you're moving. Static equilibrium, force is balanced, but you stay at rest. Finally, we talked about Newton's first law. Also, we call it the law of inertia because it relates to this whole idea of not wanting to change motion. And there's two aspects to Newton's first law. One of the aspects says, hey, look, an object at rest, what does it do? It wants to stay at rest. That's what it wants to do anyways. It stays at rest. The desk right in front of Stephen is at rest. What does that desk want to do? It wants to stay at rest. It doesn't want to move. Now, it will move if I apply an unbalanced force on it. But only if there's an unbalanced force on it. Not a force, an unbalanced force. Stephen, push on that desk for a sec. Not moving. Stephen's applying a force. Why isn't it moving? Because it wasn't an unbalanced force. When we both push on it in opposite directions, the forces are balanced. Okay, an object at rest wants to stay at rest until acted upon, not by a force, until acted upon by an unbalanced force or by a net force. Notice?
You're pushing it together. What's the energy from the push go like trying to escape both sides?
No, it's a good question though. Where does the force go? Like we're trying to do work on this desk. Where's it going when I'm pushing one way, he's pushing the other way? Do it again. What's the force doing if it's not causing motion? What are the two things a force can do? Accelerate the object. Is it accelerating this object? No. What's the other thing it can do? Deform the object. So that's what it's doing, is deforming that desk. Now, not a noticeable amount because we're not pushing hard enough, right? Okay, but in the end, You know that if we push hard enough on that desk, we'll make a measurable, a noticeable change in shape of that desk, right? You put it in this, heavy-duty vice grip, and you're going to crush this desk, right? So we don't say the energy so much goes out the sides, but it does squish a little bit, and it probably gets a little bit longer as it gets thinner in the process. What's the other aspect of it? Well, an object at rest stays at rest forever until acted upon by an unbalanced force. An object in motion stays in motion. Look, I told you I was driving a Grand Prairie. I was traveling 100 kilometers, 110 kilometers per hour, constant speed most of the way. There was multiple forces acting on the van, but those forces balanced. An object in motion stayed in motion. The car stayed in motion, or the van stayed in motion, because there was no unbalanced force acting on it. Stays in motion in a straight line at a constant speed. So the van didn't speed up or slow down. It didn't change direction until I applied an unbalanced force on that van by putting my foot on the brake, or by putting my foot on the accelerator, or by turning the steering wheel to cause a change in direction. Does that make sense? So our homework that we assigned on Friday was page 142, number 1 to 4 and 6. Any issues with any of those 4 questions? Sorry, any of those 5 questions, please. Question number 4, we just did the demonstration, right? Apply Newton's first law and the concept of inertia to each of these situations. How could you remove the newspaper without toppling the plastic beaker? What's the answer to the question? Pull it fast, right? We want to overcome that force of friction so that the net force acting on the beaker is 0. Okay, that's the key to keeping it at rest. Don't apply a net force acting on it. Don't apply a net force on it. So we want to pull that pretty quickly so that the net force is effectively 0. Any others here? Six. Did I hear 4B as well? Yeah. Okay, let's take a look at 4B, and then we'll take a look at 6. While moving at a constant speed on a level snowy surface, a snowmobiler throws a ball vertically upward. If the snowmobile continues moving at a constant velocity, the ball returns to the driver. Interesting. Did you know that would happen? If you're going at a snowmobile at 80 kilometers per hour and you throw a ball straight up in the air, it will come back down right in front of you, as if you're not even moving. Did you know that?
I do that.
When you're driving in a car and sometimes you throw something to somebody else, right? Hey, hand me the remote control for the DVD player or whatever, and you toss it. It's not flying at 100 kilometers an hour, is it? It's as if the car's not even moving, right? It's the same deal. So why does the ball land ahead of the driver if the snowmobile stops? Why, if you all of a sudden stop, it doesn't come right back to the driver? Yep. Yeah, it's all relative motion though, right? When you throw something in your car, gentlemen, it's moving relative to you, or it's effectively not moving relative to you, right? It's as if you're at rest. But relative to the ground, it's moving at a pretty good rate, right? Depending upon how fast the car is moving. If you throw it out the window in the absence of air resistance, then it'll keep moving with the car. But with air resistance, at that speed, 100 kilometers an hour or so, air resistance becomes pretty big, right? So all of a sudden, now you throw that object out the window, it wants to keep going with the car, but now there's an unbalanced force on it, which causes it to slow down pretty dramatically and pretty quickly. If you ever put your hand out the window, like you see that, right? You see how much air resistance is. So good question, but what's the answer to this question? Why you throw it up, it keeps going with you, but why when you stop, all of a sudden it lands way ahead of you? Yep. Let's not use the term momentum. We haven't learned that yet. We briefly talked about it during the review, but it's not really a physics 20 term. But you're on the right track. Definitely on the right track. Yep. Yep. So neglecting air resistance, okay, in the absence of air resistance, when you throw this ball up, you're giving it at a vertical velocity, right? But by virtue of the fact that the snowmobile was moving, it's got a horizontal velocity as well. If all of a sudden the snowmobile stops, then that's an unbalanced force on the snowmobile, but there's no unbalanced force acting on the ball, right? So the ball keeps going up and then back down, but also keeps going forward at the same speed as the snowmobile was. So this might be, you might not have ever thought of this before, but you're in that snowmobile, you throw that ball up, relative to you, okay, it goes straight up and straight down. What does it appear to the guy on the ground? I'm standing over here beside the snowmobile. What does it appear to me? How does the motion of the ball appear to me? Yeah, exactly. That's what the ball looks like to me on the ground. To the guy in the snowmobile, this is its motion. To the guy on the ground, this is its motion. But if the snowmobile stops, this ball keeps doing this, right? So the snowmobile is stopped over here, but the ball ends over here. It has inertia. It's traveling forward. It's not going to stop traveling forward until acted upon by an unbalanced force. What was the other one? 6? 6? Cassie, was that 6 you asked for? Hey. Imagine you're the hockey coach for a team of 10-year-olds at a hockey practice. You ask the players to skate across the ice along the blue line, which, for those of us who aren't in Canada, we'll explain what the blue line in hockey is. It's the line that's closest to the net. So we shoot this puck into the empty net. Most of the shots miss the net. The faster the children skate, the more they miss. Newton's first law would help the players understand the problem, but a technical explanation might confuse them. So we want to create an explanation that would make sense to 10-year-olds. Anybody? You guys are like 15, 16. You guys should be able to explain this to 10-year-olds, right? Why is it that, let's draw this out here. Why is it that if this is the net and the goal line, and we got the blue line over here, we got a puck right here, as the skater is skating towards the puck and takes a shot, why is it that the puck ends up going over there? He shoots right at the net, right? He's aiming straight at the net. Why does it end up going over there? Yep. Good. If the player is at rest when he shoots it and fires it straight this way, aims straight this way, then it's going to go straight that way, right? But if he's got a velocity to the right as he shoots it, and he aims this way, then the net velocity or the resultant velocity, this is like a problem from last unit, right, is going to end up being this way. So the puck is going to go diagonally as opposed to straight. Basically what we're doing is giving the puck an initial velocity toward the net, but an initial velocity horizontally away from the net as well. Okay, and as long as there's no net force acting on that puck, then it's going to keep going diagonally. Right? Let's take a look at 6B. With the aid of a diagram, design a drill for the team that would help the players score in this type of situation. Well, what do you got to do here? We almost did this already. Looks like that blue line's going right into the puck, right? Or sorry, right into the net, right? Well, it is. If the puck is right here, so what's your drill got to do? Yep. Okay, so you could aim somewhere different to compensate for that, or, that's a good answer, or the alternative is to shoot earlier, put the puck in a different place to shoot. Both of those are just as good as each other. Yeah. Right? Good? Any other issues with those questions? No.